Today we have a discussion about the optimal angles of diffuser, about calculation, about some aspects that have been asked for this meeting. And I will try to explain better about theta-beta M relation and theta-beta M diagram. So the theta-beta M diagram is usually appearing in the coordinates of the angle of the shock wave, which is beta, in one axis, and in the other axis is theta, angle of the body. The axis of the angle of the body is starting from 0, and the axis of the angle of the shock wave usually is not starting from 0, it's starting from some positive value. For example, for asked Mach 2.5 is something close to 20 degrees. And this is the function we may see in the book. This function actually is having two solutions, as you may find, for each body angle. For example, for theta relatively small, we may see one solution which corresponds to so-called weak solution, and another solution is a strong solution. So when you are solving theta-beta M relation as a mathematical function, you can see something this in the Anderson book, is giving to us two solutions: weak solution, lower, smaller value of beta, and strong solution, higher value of beta. It's happening for all the theta angles starting from 0 until some value of critical value of angle of the body, which we call theta maximum. This is the maximum possible angle of the body on which oblique shock wave can appear. So when we have a body of this theta maximum, we already are having maximum possible beta and maximum possible angle of the shock wave. If we increase this theta a bit more, this oblique shock wave will not happen anymore, and we will start to have a normal shock wave. So once we are working with such a no solution in theta beta M relation, you can see there is no intersection here, so there is no solution for oblique shock wave, and only normal shock wave possible. It's well described in the Anderson book. I just repeat you something from the theory. So optimization of the diffuser is always happening in the region where we can see two solutions, one weak solution and one strong solution of the theta beta M relation. So which solution you choose? You choose, of course, smallest possible beta is the realistic value of the inclination of the shock wave. Once you will try to choose a bigger value of beta is something close to 90 degrees. Here is 90 degrees already, is very close to a normal shock wave. Is usually this inclination of the shock wave is happening when we have a flow separation, when we have a lambda shock wave, etc. So it's a very specific point, very specific case. Okay, so this close to 90 degrees solution we do not consider as a real solution, and we work only with the smaller value of solution of theta beta M relation. How to determine which one is valid? You just take two roots from this equation. Numerically, you can receive two roots, and you just take a smallest root of the solution. It is possible to work with this function in terms of changing the theta angle. And also, as was asked in the question, also you can work changing the beta angle. So you basically will move in the direction increasing or decreasing beta value and looking for optimal maximum stagnation pressure ratio. In this case, also possible. It's sometimes even simpler to work with varying the beta or changing beta and then finding the theta from this theta beta m relation. Also possible, because basically the right part of this function here is just a function of Mach number and beta, so it's easy to manipulate. But also from another point of view, if you know how to solve numerically theta beta m function, for example, using method of Newton, you can also work directly with theta. And no matter with which parameter you work with, optimizing theta or optimizing beta, the final result should be the same for both approaches. Okay. When we are changing beta, in your case, we have to work only until this critical point, so or lower than critical point in this region here of beta. We can never go higher than maximum or critical beta value. Okay, or critical beta value, which corresponds to maximum angle of the body. Because in this case, we do not receive any kind of optimal solution. It will be very, very far from optimal solution. It will be very low efficiency and it cannot be considered as the optimal solution. We can see this diagram from the Anderson book as well for different Mach numbers. It's very, very similar behavior. There is some minimal possible beta angle here, which we may find for any Mach number. For example, if I open the Anderson book, I can see close to 2.5, it's between 2.4 and 2.6, is close to 24 degrees. So it's minimal 24 degrees beta corresponding to 0 theta. And this maximum value of beta which we can have is something close to 65 degrees. So when we optimizing from point of view of beta angle, we work between 24 and 65 degrees. When you solve the theta beta m relation, of course your solution cannot be complex, it should be a real number. If you receive a complex solution, probably something is not correct, because flow properties, as you know, they are all real numbers. You cannot receive complex number as a solution. P01 divided by P0 infinite is something like 0.9712. Is a quite good, quite realistic value of the losses. Okay, but we have to consider that this is just the first shock wave, first transition between infinite conditions and the first region. Okay, after you calculate this first shock wave, you need to calculate, of course, the second shock wave and the third shock wave. And then losses will be product. The total losses will be a product of every loss you receive on each shock wave. The relation between static pressure, temperature, density, you can calculate even after you do optimization of the diffuser is not the first task. First, you make an algorithm and calculate optimal geometry of the diffuser. So you define which is your optimal theta for each shock wave. And then, of course, you receive a Mach number, you receive a pressure drop, etc. And then when you have already optimal geometry of the diffuser, you calculate already thermodynamic properties and velocity. Is the last step. And you have to remember that all thermodynamic properties, pressure, temperature, density, they have to increase from one shock wave to another. Okay, and just the Mach number and the velocity, they decrease. What is very interesting also is not the law, is not obligatory always happening, but what I found with experience, that change of Mach number, if we plot in the following way, for example, like this is our infinite conditions here at the beginning. Then we have a shock wave 1, oblique shock wave 2, oblique shock wave, and then shock wave 3, normal shock wave. We can basically see a straight line like this. It's not the law, but usually the line is similar, is close to something of straight line. When you make a Mach number, here will be supersonic flow, right? Here will be Mach, also supersonic more than one. Here will be also supersonic, and somewhere here you will have a transition. So Mach 1 will be somewhere here. But if you put all these 4 points, you can see basically a line very close to a straight line. It's not exactly a straight line, but I think it's a close. It's close. For two-dimensional planar shock wave, the case which you are calculating. Okay, the Mach number behavior is like this. The pressure, temperature, and density, they are not linear, so we cannot observe such a behavior for thermodynamic properties. But just to give you some orientation, what should be the change? About an exact values of optimal shock wave and the optimal geometry angle, you can find these values in the literature. From the internet, you can definitely find the literature and find what are the optimal values for any Mach number. Basically, the theta optimal will depend on two factors. First factor is what is your M infinite, and what is the number of how many shock waves you have in your diffuser. So depend on infinite Mach number and number of shock waves in your diffuser, you can come out with the optimal angles of the shock wave. It's not depending on anything else. It doesn't depend on the altitude of flight. It doesn't depend on the temperature, pressure, basically anything. You just need to know two parameters: Mach number of the flight and the number of the shock waves you need to have, and then you can already receive optimal shock wave angles, or not shock wave, sorry, body angles. And also the shock wave angles, of course, they are related. This is very far from optimal diffuser operation. It basically we do not consider as optimal diffuser operation. So we work only with the lower part of the curve. But mathematically, you receive two solutions, so you have to separate if it's a upper solution, if it's a lower solution. You need to find minimal beta and work with this minimal beta. Do not consider another solution. For this curve, we may see that beta is always bigger than theta. Okay. So this is a general relation. So your beta, the angle of the shock wave, is always bigger than the angle of the body. And physically you can see it, right? If we go back to this small schematic which I plot here, which I made here, because the angle of the shock wave is outside of the body. So this is why beta is always bigger than theta. And this is quite obvious from physics, right? But mathematically, you have to consider. So this is one more checkpoint you may have in your system. If you receive beta bigger than theta, that's okay. If you receive a beta smaller than theta, maybe something is wrong. So take a look carefully about this question and make such kind of check in your calculation. In different books, this theta-beta M relation may look differently. It's expressed in different forms. For example, there is an aeronautic book from ETA, basically a kind of translation of part of aerodynamics of Anderson, and beta is a main parameter, right? And I think it's a bit rewritten in a different form.